The topic for the day is sparse matrix. So a sparse matrix is a matrix in which majority of its elements are zeros. These matrices are used in applications where data is stored in tabular form, but most of the entries are irrelevant or empty, and those empty values are basically represented by zeros, and we have a lot of them, right? So what are the key characteristics of a sparse matrix? First, as we discussed, that it would have high proportion of zero elements. Sparse matrices contain a significant number of zero values as compared to non-zero elements. Efficient storage: instead of storing all elements, sparse matrices use specialized data structures to store only the non-zero values and their positions. Since we'll be storing only the non-zero values, we must know what is their position in the matrix. So all would be discussed ahead in the implementation part. For the time being, let us move to the next point, which is regarding memory optimization. So reducing the memory required for storage by avoiding storage of unnecessary zero elements. So as I said earlier also, that will be storing only the non-zero elements, not the zeros. And since there are many zeros, so their space is not required. So what could be the examples of sparse matrix? So a graph adjacency matrix. In a graph with a large number of nodes, few edges, the adjacency matrix is sparse because most node pairs are not connected, as you can see in the diagram, right? So we are taking the diagram of a graph in which we have shown the nodes as A, B, C, D, and E, while the edges are represented by the arrows between the nodes. So here you can see an arrow from A to B. It means that there is a path between A node and B node. That means they are connected. So if you can run here for a moment. So if you are seeing a 1 here, it means that there is a path between A and B, right? Similarly, a 1 here would represent that there is a path between B and C, right? But most of the nodes would be connected to each other, and that non-connectivity is represented by zeros in this matrix, right? Talking of another example, we can say an example of a movie recommendation system. Users cannot view and rate every movie because there are 1,000, even millions of films and millions of users. So this data may be shown as a matrix with the movies in the columns and the users in the rows like this. So user 1 has seen movie 1, no. Same for movie 2, he hasn't seen or she hasn't seen. User 2 has seen the movie 4 and he or she can rate it. Similarly for user 2 and when compared to movies, so there would be a lot of zeros, right? So examples of sparse matrix could be scientific simulations where matrices representing physical systems like finite element analysis. Recommendation systems, user item matrices where most users do not interact with most items, as we saw in the previous slide. Example could be Netflix or Amazon recommendation systems, right? Similarly, another example could be the natural language processing where document term matrices where each document contains only a subset of the all possible terms. Implementation part. So we have basically three kinds of implementations: array implementation, the YAL format implementation, and the linked list implementation. We would be taking up array implementation straight away, and the other two implementation would be discussed later, right? So here you can see a sparse matrix where we have lots and lots of zeros and a few non-zero elements. So what is the way of storing them in a specialized data structure, and what would be the structure of that specialized data structure, right? So would be for each non-zero elements like this 5 would be storing the row index of that value and the column index of that value and the value itself. So for this 5 I would be storing this 0 because this is the 0th row, and this 2 which is the column index, right? So this 5 is basically stored at 0th row and 2nd column. Similarly, this 8, as you can see here, is stored at 0th row but 6th column, right? Here you can see it. And one more thing, since there are 2 elements in the 0th row, you can see 2 entries for 0. Similarly, 2 entries, as I can see, for 4, you can check it here. For 4, you have 2 entries like 7 and 8, right? Similarly, for 8, you have 2 entries. That means row number 8 would be containing 2 non-zero elements, right? There could be 3 entries, there could be 4 entries, and so on. So in this example, we have a max of 2 entries for 0th row and 4th row, and the 8th row. Rest are having only 1 entry because there is only 1 non-zero element in those rows, right? Now, implementation wise, we would need a composite data type like a structure variable or the structure data type to store these 3 values. That means row index, column index, and the value. So for that, R has been designated to store the row index, C for column index, and the val value for storing the value, right? Right. So as far as implementation is concerned, as we would be moving to the code shortly, we would need a vector which would be consisting of 3 members, right? So if this is an array, but this would be an array of 3 members per row or per entry, right? So this 0 represents this, as I told you earlier also. This 2 is this 2, and this 5 is this 5. That means the value in which row it is, that is stored here, that is pointed to by this arrow, and column index has been pointed to here, and here is the value of 5, right? So moving on to the code, we basically need a structure variable, as discussed earlier, to store 3 values. So this would be a 3-member structure variable, right? N has been defined as 100, as you would see shortly. Like here I have written mat n by n, it means 100 by 100. Obviously it can be any value this size n, 20 or 10 or 15 or anything like that. For storing the number of rows and columns, like in this case we have 9 rows, in fact 10 rows and 7 columns, because the indices start from 0. So 0 to 6 is 7, 0 to 9 is 10. So in this matrix you have 10 rows and you have 7 columns. So R would be 10 and C would be 7. This SMR we would see later on. So matrix is mat is this matrix. The actual matrix we store is the sparse matrix. Then we have a vector that we just discussed. This vector is again of the size of n, right? So which would be storing our this row index and column index and the value itself. So this function would be basically scanning the matrix. What I would be passing on as argument to this function is the mat matrix and the row and column, that is order of the matrix. Similarly, you can of course print the matrix also by passing the same set of arguments. Then importantly, we have the create sparse matrix function where I have passed mat, that is this matrix, and order in terms of rows and columns, and sm means this. So this vector would be filled up the way I discussed in the previous slide by this function, right? So let us first see. So what would be the code of the scan function? It would basically need the 2 for loops and would be scanning the matrix element. Similarly, for print matrix, we would again need 2 matrix, as you would be aware that in to store or to print the 2-dimensional, you would need the services of 2 loops, right? So here I am printing, here I am scanning. So these would be the 2, at the end of which would have this matrix scanned or inputted by the user, right? So now to the important part, which is to create a sparse matrix vector, right? So I would be scanning, again I would be using the services of 2 loops, for loops. In this case you can use any loop, of course, right? So here I am saying if there is a non-zero element. So while traversing obviously from row number 0 across the columns, right? So I'd be saying, for example, in this matrix, I would reach the point of this 5, where I would be 0 and J would be 2. So my mat 0 2 element would not be equal to 0, right, because it is 5, right? What should I do next? I should store in this vector for which the indexing has been assigned to k. So k starts from 0. So sm k means 0 dot r member would be equal to I. That means it's 0 because I am currently on row number 0 and I am currently on column number 2. That has been assigned to the c member of the vector, right? And the val of that vector would be, and that means this value, this 5 would be equal to the current mat ijth element, which of course is the 5, as I just told you, right? So this first entry has been entered in this vector, right? So of course what I would need is to increment the k variable so that the next entry would go down here, right? Now SMR is basically keeping track of the number of rows in this vector or the number of entries. As you can see here, SMR has been initialized to 0 while coming to this function or going into the loops. So every time we do this entry, just like we did for this row 0, 2 and 5, SMR would be incremented, and the whole process would go on. Say for this 8, this if would be true for the I value of 0 and j value of 6. That means when I am on row number 0 and I reach the column number or the j value of 6, this would be true, because the mat ijth in that case would not be equal to 0. So we have found another non-zero element. So we would make another entry into the SM vector, right? R would be 0 and C would be 6. Val would be 8. So this entry is done. Again we do the k plus plus and SMR plus plus. So at the end of this all, while entering these entries into the SM vector, would be returning with the SMR, means total number of rows in that SM vector, right? What next? Next is to print the sparse matrix. Very simple. Now we will have to print this vector, right? For that we'll go from 0 to R. Now remember, here I have passed SM. You can check it from the main function. I have passed SMR to this function and I have stored that SMR value into R, right? So this R is a local variable which points to SMR, which we generated in the previous slide, right? So now I'm saying traverse from 0th row to the total number of rows in this vector, and in the meantime go on printing smi.r and c value and this, which would of course print this vector or the entries of this vector, right? Now the sparse matrix implementation linked list part, right? So linked list for the same set of values or the same matrix for which we generated this SM vector using the array implementation. Let us do it for the linked list implementation. So for the linked list implementation also we would need the services of a vector, but this time of a different kind. This vector would be storing addresses, right? So here would be storing an address, here would be storing an address, here would be storing address, and for all the other entries would be storing addresses of what? That would see, right? So this vector has been named as 0. So this is, for example, 0th element, 1, 2, 3 and so on, right? Now concentrate on this. So this 0th row has how many entries? 2 entries. So you will have 2 entries. So this is a node, as you would be aware of the node if you have studied the linked list or the stack or the queues implementation, linked list implementation. This node, if I can get this, so this node is basically storing your column index and the value, column index and the value. Why not the row index as in case of array implementation? Because I am storing these nodes with respect to the 0th cell of this X vector, which would in turn mean that you are basically referring to the row number 0. So row number 0, so this effectively would be 0 to 5, which is what you are seeing here. This would effectively mean 0, 6, 8. That is what you are seeing here, right? So implement linked list implementation wise, this would be a node whose address would be stored by this cell. That means x 0th. That is why I was saying this x 0th cell, or all the cells for that matter, would be storing addresses of certain entities, and that entity is the node itself. Node is nothing but a variable of structure type that would be seen in the implementation. So for the time being, just remember that we are creating a node with 2 values, in fact 3 entries we will have to do. First represents the column entry, then the value, and next is a pointer again, which would point to the next node if there is one. So in this case, for this vector x0 entry, or the 0th row, we have two entries, as you can see here, 0 to 5 and 0, 6, 8. 0 to 5 is this, and once we create a next node or the subsequent nodes, those addresses we will have to assign to the previous node or nodes, right? So the address of this node would be stored by this, whose address in turn would be stored by this cell, right? 0th cell. So for 1 here, or row number 1, we have only one entry. That is what has been shown here. So this effectively is 1, 5, 3. That means row number is 1, 5 is the column number, and the value itself is 3. Same for 2, same for 3. Now for 4, we have 2 entries here, right? So 0th column, in 4th row you have an element of, or the value of 7 at 0th column, and you have a value of 8 at 4th column, right? Same way you can do for others. I hope you are getting. You can of course pause the video and do some sort of hand simulation also, right? Now on to the code part, or the implementation part in terms of C programming. So we need a struct node, right, which is storing the column number and the value, and the third member is the pointer, as I was alluding to in the previous slide, that this member would be storing the address of the next node if there is one, right? So I have done certain, this is the x, this is the x vector I was talking of. These t and p would be temporary variables, as would be seeing. So let us take this x again, and this x has been assigned the indices of 0, 1, 2 and 3, or these cells have been assigned those indices, right? I am again taking the same sparse matrix, and the create sm is that function which would be creating my structure in which I would be storing those values, non-zero values. So what I would do is, for every non-zero element I would be creating a node, right? So malloc size of struct node, right? And the node which has been created would be allocated at some address that has been assigned to p, right? Now for p's C member, I would be assigning a value of j, because j is representing the column. If you can recall, again I would say that suppose the control has reached to this point, that means I would be 0 and j would be 2. So I am assigning, you can see here, I am assigning the C member a value of 2, that is j, and I am assigning the V member the value of mat ij, which in this case would be 5. That is what I have seen. For the sake of understanding, I have assumed that this node has been created at 0, 0, 0 address, right? Of course it is hypothetical, right? So P, the link member of P has been assigned a value of null. So this member has been assigned null because it would be storing the address of next node, which obviously hasn't originated yet or allocated yet. So of course it should point to null for the time being, right? So for the time being, we have come to a point where we have allocated a node at the address of 0, 0, 0, and 2 has been stored in the member C, 5 has been stored in the member V, and this part, link part, has been assigned a value of null. But do you think this node is linked to this X vector or any of its cells? No, not yet. Right? Now remember that every time you create a pointer variable, the default value for that pointer variable is null. So why I'm telling you this is that when I created this X vector, X0 would be null, X1 would be null. That means all the cells of this X vector would be equal to null, right? Because this X vector has been declared as pointer, right? Of course, of the type of struct node. Why? Because it would be storing the addresses of nodes, right? So now concentrate on this line of code. If X0, because I would be 0 still, because we are here, right? Where I is equal to 0. So if Xi is equal to null, is it true? Yes, it is true, because there is nothing, there is null here. So Xi would be assigned the value of P. But I assumed P to be, yes, 0, 0, 0, where the new node has been allocated. So this 0, 0, 0 would be stored in the X0th location. So that created a link from what? X0 to this node, right? For the time being, we would not touch this else part. Let us go to the function again, for example, or the loop again. So it would be, I would be again 0, but j would move to this until it reaches this 8. Now this condition would be true because we have found another non-zero element, which is 8. For that, we would be allocating another node, right, like this, and again assuming that some fictitious address 111 has been assigned to it, or the node has been allocated at 111, right? So again we would be storing the j value in the C member, which is this 6, and the value were 8, right, in the val part or the V part of this node, and of course this link part would be null, right? Now if X ith is equal to null would be false at this point of time, because we have some address over there, so the control would go to the else part, right? Now we need to reach to this point because there is already a node there. We should reach here, and from there we should store the address of 111 in here, right? So for that I have done what? I have used a temporary variable which has been assigned a value of X ith. What is X0? It is 0, 0, 0. So T would be pointing to this node because Xi is 0, 0, 0, which kind of points to this node, right? And I'm saying while T's link not equal to null. Now remember here that we cannot write while T not equal to null as you would have done in case of data structures or the linked lists. So we need to check if T or the node to which currently T is pointing to, its link is not equal to null. Now remember here that we have a null here. We have a null here because this node has been created, but we have not assigned code wise because we have not reached it to that point where we have assigned this address to this link part of the previous node. So what I would be doing, I would be reaching to that point. Now look at this. We have reached it to that stage where T's link part is equal to null, right? That means this condition has failed for the very first time. So the control won't go inside loop for once even, right? So I would be coming to this line of code where T's link part is equal to P. Now remember, every time we create a node, P would be pointing to that node. So P currently is pointing to 111, right? So that 111 has been assigned to T's link. What is T? T is 0, 0, 0. So T's link, that means 0, 0's link part, that means this member would be now pointing to P, which has been shown here. right? So this way the I loop would be done and dusted, and we would be taking the in fact j loop. So j I would be now incremented to 1. That means we would be now concentrating on row number 1. So once control reaches this point we have found the non-zero element, right? For this we'll create another node. We'll store the column address of 5 here and the value itself here, right? And this would be pointing to null because there is no node adjacent to it, right? You can hand simulate the code yourself, right? So for other entries would do the same. Of course I have used the fictitious addresses for the sake of understanding. So this, and lastly for row number 9, right? So as far as displaying this vector goes, I would be doing for same set of values. Look here, for this for loop, since this is a one-dimensional vector or array, so I would need only one for loop I have used here. So R would be pointing to the number of rows, which is equal to 10, 0 to 9. Right, now I have started from xi means this, as we saw previously that this x is, we would be storing the address of this node, right? So that is where I have started from. This xi, that means 0, 0, 0 would be put into t or stored in t, and I will be saying while t not equal to null. What is currently t's value? The value of t would be 0, 0, 0, the fictitious address of this node. So what would it would be printing? It would be printing the row number, the column number, and the value. That means this 0 and this 2 and this 5. So we have reached it here. Now t should now point to t's link. So which is t would be now equal to the link part. Link part, as we just discussed, would be currently holding the address of this. So it would, the while loop would be repeated for this set of values, right? 6, 8, and the row number would be printed. Next t would be incremented or updated to t's link. What is t's link? Null. So it would go here, the condition would be false. So it would take now, I would take now the incremented value of 1, and t would be initialized with x1. That means here the address stored here, which of course would be the address of this, and it would print the entries of 5 and 3, or the 1 also, row number, right? And t would be updated to this link part, which is null. So for this row it would be simply printing the contents of only this node. Then I would be incremented to 2, and the contents of this node would be printed, and same for other nodes, right? On to the next implementation, which is the YAL format implementation, right? So for this matrix, what would be the way of storing the non-zero values as far as YAL format is concerned? So I'm taking a matrix, namely M, right? So we represent a matrix M whose dimensions are M into N by 3 1D arrays or the vectors, right? Those 3 vectors are named as A, IA, and JA. How are they stored? Let us see. The A vector, that means this vector. The A vector is of the size of the non-zero elements and stores the non-zero values of the matrix. The values appear in the order of traversing the matrix row by row, as you can see here. So start from this 1. Remember that these are the row indexes or indices, and these are the column indices, right? So our values are stored in the non-black color, right? So this would be the 1, first non-zero value, then followed by 3, and then 7, then 2, then 5, 9, 3, and so on up to 6. So that is what we store in this A array. So the non-zero values of the matrix would be stored in this one-dimensional vector, which is named as A. Then is the turn of the IA vector. it is of the size of m plus 1 and stores the cumulative number of non-zero elements up to and not including the ith row, as you can see here. So firstly, 0 means there are no, to begin with, there are no non-zero elements. Then in the first row you would have 2, right, because we have 2 non-zero elements. Then going up to row number 1 you have 2 more, so cumulative would mean previous 2 plus these 2, so that would make it to 4. Then in the row number 2 we have 3 non-zero values, that is why the count has gone up to 7. And then final row contains only 1 non-zero element, that is 6, so the count has gone up to 8, right? So lastly we will have the JA vector, which stores the column index of each element in the A vector. Thus it is of the size of A also. So 0, 1 means the first element is at the 0th column, then the next element is at 1th column or column number 1, next is at column number 1 again, that is why this 1 has appeared again. Then you have 3, because the next non-zero element is at the column index of 3. Then any guesses? Yes, this 5 is at the column of 2, so this 2. Then you have 9 and 3 at 3 and 4 column numbers respectively, and this last value is at the column index of 5, right? So this was the JA array.